is being publicly streamed.
Let's say you have so what he was explaining is that in R3, let's say this is your R3 space. So x-axis, y-axis, and z-axis. So what you do, you take a parallel copy of your xy. Okay, you take a parallel copy of xy plane. So this is a parallel copy of xy plane. At some z equal to z0.
Okay.
Now we define. So there can be two vectors. So you take two vectors here. Okay, there can be two vectors like this, and then you look at the projection. So you can define addition. So this is a subset. First of all, this is a subset of R. So this is a subset of R. Right? This is a subset of. So now what I want to do, I want to define a vector space structure on it. That means I need to give a definition of addition. I need to give a definition of scalar multiplication. And the way I define scalar multiplication and addition is that you take any vector, let's say v1, v2 in this plane, and then you look at the projection. So you look at the projection. So you look at two vectors in this plane. So these are the two vectors. Okay. So any point in this subset. So if you look at any points of this subset, that means v1 and v2 are 2 points in this subset. So we will call them vectors of this subset, and then you project them. You project them onto the xy plane. Okay, so they will project, let's say, onto something like this, and this will also project onto something like this way. So let's call them the P of V2, P of V2. Right. Now you can define addition over here. So what is the addition?
Yeah, for the projection, right?
Yeah, for the projection.
Okay.
You define the addition over here, and whatever the new vector that you get over here, let's say V3, which is the addition of these two vectors, you look at the image. You look at the point which project to this V3. Okay, so in this case, let's say this point will project to V3. So this point will project to V3. So this will be the addition of, so let's call it V3 prime. So this V3 prime vector will project to V3, and it is a point in the subset. Similarly, for scalar multiplication also, you take a vector, you take its image, you take its projection, and you multiply the constant or scalar by that vector, by that scalar, and then you look at the pre-image, wherever it hits, wherever it lands, and then you look at the what vector in that subset will project onto this one. So this is how we define. So now how to see it mathematically? This is a geometric picture. Okay. And you can check that this is a well-defined addition and scalar multiplication. Okay. So what do I mean by well-defined? That means if you take any 2 points in this subset, their addition will be closed by this operation. And similarly, if you take any point in the subset, its multiplication will also be, scalar multiplication will also be closed under this operation. Now, how do I?
Excuse me, sir.
Yeah.
So can you repeat this, sir? Actually, I didn't understand anything.
Yeah, so I'm basically discussing a doubt asked by you. Asked by Anurag, I guess. I'm discussing that. Arnab, sorry. I'm discussing the doubt asked by Arnab. So yeah. So in the lecture, I think it's 3.2, right? Lecture 3.2. Yeah. So lecture 3.2. In one of the videos, the professor discussed about affine flex. Okay, and he describes affine flex as the parallel copy of xy plane in R. Okay. All right. So this is a parallel copy of XY plane in R. So this is a parallel copy of XY plane in R. Okay. Now, how do we define the addition? So we define addition like this. You take 2 points, let's say V1 and V2 in R in this affine flat. Let's call that S. Take 2 points at V1 and V2 in S. And then what you do, you project V1 onto XY plane. So you project it onto XY plane, right? So, and you also project V2 over XY plane, and you consider their addition. So, yeah. So V1 plus V2, projection of V1 plus V2 in XY plane is equal to the addition of projection of the. This is how you define the addition. Okay, a vector whose projection is nothing but the sum of the projection. Now, projection of V1, V2 will be in XY plane, so it is well defined, right? Because XY plane is a vector space. It is a subspace of R3, it is a vector space in itself. So it is defined. So you can pull there. So you can now look at the image. So in this example, let's say V1 and V2, their projection is on PV1 and PV2, right? This is the projection, and then you look at by parallelogram law, you can find out the addition of these two vectors on plane, and then you look at the vector, you look at the point in the affine flat which correspond to, which projects onto this vector V3 in XY. So that point you define it to be the addition. Okay. Now, how do I write mathematically? Okay. So what is happening here is that, can anyone tell you what will be these? What is this subset? What is this? How do I describe this subset? If it is a parallel copy of XY plane at Z equal to Z0, then how do you write it mathematically? Can anyone guess?
Excuse me, sir.
Yes.
Sorry to interrupt, sir. Sir, I don't know what you are asking, but I have one doubt about this. Can I ask?
Let me finish this up, then we can.
Oh, sorry, sir. No problem.
Yes. So, yeah. Can anyone want to guess what? How do you describe this subset?
So Z is equal to Z1.
Z is equal to, yeah, Z1 is there. Yeah, that is correct. Z is equal to Z1. But what is that? If you want to write down the vectors of this, the points in this, how will you write down? So it is XY can be anything, but Z1, Z is the fixed number. Z1 is a constant, right? So instead of that, we write it Z is equal to some K. K is a constant or a scalar, and XY varies it, right? All right. So this is your subset S. This is your affine plate S. Now, can anyone interpret how did I define the addition that I defined? Just defined. Can you interpret this in terms of the mathematical symbols? For example, if you take two vectors.
Yes, sir.
Yeah. How do you define that?
Like suppose we have two vectors, vector v1 and vector v2. Vector v1 has the coordinates x1, y1, z1, and vector 2 has the coordinates x2, y2, z2. If we try to,
will it be z2
yes,
and z1? Then if it is an S, it is an S. If it is an S, then what will be the Z coordinate? It is always fixed. Z coordinate is always fixed.
yeah, it will be same like z1.
Yeah, it will be. I've taken K, so it is at Z equal to K, so it will be K, right? Then Z2 will be K. Okay. Yeah. Now, how do you define the addition?
Then the projection of v1 plus v2 will be defined as x1 plus x2, y1 plus y2, comma 2k.
No.
It will be K.
Projection of this will be just, what will be the projection of first vector?
X1, Y1, 0. X1, Y1, 0.
Yes, X1, Y1. What about the second vector?
X2, Y, 0.
Now you add them. What is the addition?
X1
It is
plus
x1,
Y1
x1 plus x2, y1 plus y2, 0.
and 0.
Right. Now you look at the image. What will be the corresponding point? Whose that point? If you project onto xy plane, you will get this. What will that?
0 will become K and the rest will remain
Exactly.
same.
Exactly. So yeah. So you are defining your addition. So this is a special type of addition. It's not the usual addition. Let me circle it out. So it's addition that you are defining on this affine plane. Okay. So you're defining it to be like this. All right. Similarly, you can also define a scalar multiplication like this. Just a minute, Sakshi. I will come to you. So if you take a point and you multiply the scalar, then what you are doing, you will first project it to xy plane, which will give you this. You multiply your scalar, you will get Lx, Ly, 0. And then you will look at the point which you will get, which will project onto this one. So that point will be exactly this. So this is how you're defining the scalar. So your scalar multiplication. And this is your addition. Now, with respect to these two operations, you can check that S, the affine flat, is a subspace. It's not a subspace, it is a vector space. Okay, it is a vector space, not a subspace of R. It will be a vector space. Okay. Yeah, Sakshi, you may go on.
Thank you, sir. Sir, maybe I don't focus properly on the lecture. Can you please explain that part? Why k equals 0?
Because you are taking a projection onto the xy plane. If you take a projection of any point in R3 to xy plane, then what happens? Which coordinate will become 0?
Z coordinate will become 0.
That's what I did, right?
Okay, for the why you take sorry sir, the way you take xy plane, that is why, that is the reason z equals 0. Okay.
Yes.
Okay.
Because
Thank you, sir.
because the way it is defined, you need to project the addition is defined as. Is it
Sir,
clear now, Arnav?
sir, just one doubt. The way it is right, project xy. Can it will ask project yz zx?
Yeah, that can be done. It is simpler. It is same thing. You can have a plane which is parallel to YZ plane. Okay, and you can that can also be defined as a affine plane. Okay, by projecting it onto the YZ plane, and then you can do the same thing. You can define operation with a similar. Okay.
Okay, thank you, sir.
Sir, so can we say that affine flats are also vector spaces? Or
Affine flats are vector spaces because you have given the operation. You can check that. Okay, so this is an exercise for you. Check. You have this addition. Okay, this is your addition defined.
yeah.
This is your scalar multiplication. Now check all 8 properties, whether it follows the commutativity, associativity, and then distributive law. All right, all these properties. Then what will be the zero element? What is the zero element in this case? Can anyone guess?
The 0 element.
Yeah.
Sir,
Z element.
Can you
So what will be zero
one
vector?
time figure? Sir, figure can you explain one time, please?
No, what is a zero vector in this case?
Z vector is 0 vector.
No. What does it even mean? What is Z vector? What do you mean by Z vector?
So zero vector is 0, 0, k.
Yes. Yes. At least someone is focusing on the lecture. So thanks. Yeah, if you want to, so someone asked me, can I repeat the figure? If you want me to record, if you want me to revise this, so it's better after we finish the lecture, you can go back to the recording. Lecture is getting recorded. You can check it out on the YouTube also, and you can also go through this. I've already explained this figure, so I'm not going to do that again because it will be then doing the same thing twice, which is not good because I need to cover material also. Okay, so Arnav, your doubt is clear? Okay.
Yes, sir.
Are we good to go now? Okay, cool. All right. So there is one more thing. So last time someone asked me if I have a homogeneous system of equation, and then the number of equations are more than number of variables, do I always get a unique solution? Right? Someone asked me that. I don't remember who asked me. Is that person here?
Actually, I only asked that also.
Oh, you only asked that. Okay, okay.
Yeah.
So, right. So, Arnav, that is not true. You can have a system of, I might have said yes to that thing because that was, you asked in the very late. So for example, you have, let's say, consider this system of equation. Okay. And so this has how many equations? It has 3 equations, right?
Yeah.
And how many variables are there? 2 variables. But does it
Yes.
have a unique solution?
I mean, it's a homogeneous, so trivial solution should always be there.
Yeah, that is already there. But is that the only solution? That is the question, right? Is it a unique solution? Zero solution is unique. Or can there be any other solution?
There can be any other solution.
Right.
So there can be infinite solutions.
There are infinite solutions, right? How do you see that? You just write it into the coefficient matrix, okay? 2, 2, 1, 1, 3, 3. And then what you do? You can, now this is a system of linear equation. You can write down the augmented matrix and you know how to solve an augmented system of linear equation using a matrix. Row reduction, Gaussian elimination, we have discussed this, right?
Yeah.
And then you can obtain the RREF form of this matrix. What will you get? You will get 0, 1, 1, 0, 0, 0, 0, 0, 0, 0. All right. Now, how many independent variables are there? How many dependent variables are there?
Independent is 1, dependent is 1.
Yeah, independent is 1. Then how many dependent?
1.
Yeah, both are 1, right? So if there is a independent variable in your solution, then can you get a unique solution? No.
No.
Okay. Right? Because you can write your because a dependent variable can take anywhere, so you will get infinitely many solutions. Okay. So no, you will not get uniqueness in this case. So yeah. All right.
Sir, we can
So
get
that is
unique solution also in this case, sir.
No. What is
Hello?
what is a unique solution? If you are getting more than one solution, then that solution is not unique.
No,
Right?
no, other set of equations, sir, similar to this, which have 3 equations, 2 variables, sir.
3 equations, 2 variables.
Yes, sir.
Yeah.
So,
Yeah. Then there is a possibility, but it is not always the case. That is what I'm saying.
yes, sir.
Yeah. You can have system of equation like this, where you can have infinite solutions. So you cannot say something in general like if you have more equations and lesser variables, then you in homogeneous system of equation, then you will always get unique solution. That you cannot say. But what you can say is, if you have less equation, more variable in homogeneous system of equation, then you will always have infinitely many solutions. That you can say. All right.
Okay.
Sir, it may have no solution also, sir.
No, solution will always have.
Yeah, for homogeneous solution will always be there, but
Zero
if
solution is always there.
Yeah, but if the equation was not a homogeneous, then there no
Yeah,
solution
then there can
might
be
be a possibility.
inconsistencies. Then there can be inconsistent solution. That means there cannot be any solution. The system can be inconsistent. But in this case, we are not. In homogeneous, we will always have consistent system, and we will always find out something. All right. Okay. Now let's move ahead. All these things are clear. Now we can move ahead and discuss what we are supposed to. Okay, so in today's discussion, okay, that was a good point. That the doubt that you asked me about homogeneous system of equation. Today we will see how to solve that system of homogeneous system of equation and how to find out what is the dimension of how many bases will be there in that in the solution of that system, homogeneous system of equation. What will be the basis? What will be the dimension of that subspace in R? So today we are going to discuss that. That was a good point to start with. All right. So now let's start with this system of homogeneous system of linear equations. So yeah, so can anyone tell me how many equations? There are 2 equations and then 3 variables. So how well? So what can anyone tell me what will the coefficient matrix will look like? How the coefficient matrix will look like?
3, 4, 3, 1, 1, 1, right?
Yes. All right. This is your coefficient matrix. Now we have already seen that you can write any system of linear equation as in terms of the coefficient matrix, which means that A multiplied by with x y z equal to 0, 0, 0, 1. Okay. Sorry, 0, 0, 1. Not 0, 0. Because I have 3 cross 2 matrix, so it will be, sorry, 2 cross 3 matrix. I will get 1 cross 2, 2 cross 1 as the answer. All right. Now, question is how to find solution to this system of equation. Now we have seen methods. Like what are the methods that we have seen? We have seen Gaussian elimination. All right. So how does the Gaussian elimination work? You have a system of equation. You write down the augmented matrix, and then after writing down the augmented matrix, you perform row reductions. Okay. Now, what are the row reductions are allowed? You can interchange rows first. Second one is you can multiply a scalar to any row. All right. Third is you can add a scalar multiple of another row to one row. Okay. All right. So these are the 3 row reduction operations that we perform on a matrix. In Gaussian elimination, and we perform this elimination up to what point? We perform this elimination up to we reach a state. We reach a state so that our augmented matrix, which is of this type. So this is your matrix B, 0, 0 vector. Matrix is B. Perform the Gaussian eliminations or row reductions, row operations or row reductions. I'm using multiple terminologies, but they all mean the same thing. This whole process means the Gaussian elimination, performing row operations on the coefficient matrix on this augmented matrix. So how many columns are there? It has n rows, but n plus 1 columns. Now we perform this operation up to we get an RREF of A. All right. And then once we get the RREF form, we have n number independent variables. The leading terms become the dependent variables. The non-leading terms, the non-leading variables become the independent variables. Okay. So that process you already know. Now what we do, we try to write down the independent. We try to write down the dependent variables in terms of the independent variables to solve the system. Okay. So this is what we have already discussed. Okay. In one of the longest sessions that I took. All right. So today also we are going to discuss this. We are also going to work on this Gaussian elimination, but for homogeneous system. Okay, so it will be a simpler revision to all. All right. Yeah. So now let's work with that system. So earlier I had a matrix which was of this type. I started with this system equation. Right. This is my coefficient matrix. Now let me write down the augmented matrix of this. Okay, so it is 3, 4, 3, 1, 1. Let me write down the augmented matrix. So A, B is going to look like 3, 4, 3, 1, 1, 1, 0, 0. Okay. Now let's perform the row operations. So let me first do R1. Let me interchange R1 and R2. So I can get 1, 1, 1 on top and 3, 4, 3 on bottom. Right. Now what should I do? I will subtract R2 by 3 R1. And what will I get? 0, 1, 0, 0. All right. Now what will I do? I will perform R1 minus R2. All right. So because I want to obtain a RREF. So this is 0, 1, 0, 1, 0, 0, 0. Okay. So we have obtained an RREF. All right. Is this an RREF form?
Yes, sir.
Good. Now, once we get the RREF form, so what are the solution of this? So now let me again convert this back into the system of equations. So 1, 0, 0, 0, 1, 0. This matrix is multiplied with x, y, z and equal to 0. All right. So what does this give me? That x plus z is equal to 0 and y is equal to 0. Now, what can you say about how many solutions are there?
Infinite number.
Infinite number.
Infinite events, right? So, and let's also notice one more thing. What is the leading entry of? So both of the rows has leading entry. Right? Now, so that means the first column correspond to the first variable, which is x. Second column correspond to the second variable, which is y. So first and second column has leading entry. That means x and y are the dependent or independent?
Variable. Dependent.
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 Right. Yes. And what is the remaining variable, which does not have any leading entry?
Is Z.
Z. Right. Z doesn't have any leading entry corresponding to it. So Z is the independent variable. So what does it mean? So whenever you have independent variables, that means that you have infinitely many solutions to this system. All right. That is we already. So what are the solutions then? Minus z, 0 and z, right? And z is in, that is the solution of the above system. Okay. All right. Just give me a minute. All right. So this point is clear to everyone. There is no doubt. There is nothing new because we have already discussed these things in one of the lectures. So today also we are going to discuss this in this. So now what we have seen is that the solution of homogeneous system of equation of linear equations is similar to the solution of this type of set, right? Set of all values of x, y, z in R3 such that Ax is equal to the 0 vector. Okay, because homogeneous system of equation is equivalent to Ax equal to 0. All right, so solving this is equivalent to system of equation, right? So the solution set of homogeneous system of equation is also equal to this. And now what is this set called? This set called is the null space of A. All right, because why null space? Because it corresponds to all those vectors. If you multiply it with x, if you multiply it with the matrix, you get 0. So those vectors, set of all those vectors is called the null space. All right, so this is the null space of A, and null space of A, which is the coefficient matrix, is equal to the solution of the homogeneous system. All right, now you can say this in general also. All right, so this subspace, so the subspace W defined in this way, which is the system of equations, okay, is called the solution space of the homogeneous system of equation. Also, it is called the null space of A. So whenever someone asks you what is the null space of A, you need to solve the system of equation. Okay, and you need to find out the solutions of it. And if someone asks you to solve this homogeneous system equation, which is of this type, then also you do the same. So both are same. Okay. Now my question to you is, is null space of A. So suppose you have a matrix A and cross N. Okay. So now is this null space of A is a subspace? Is null space of a subspace?
It can be, sir.
What do you mean by it can be? So is there any possibility that it is not a subspace? Or
The subspace of Rn.
yes, so it is a subspace of R. It is a subspace of Rn. Why? Because whenever you have a matrix A n cross n, you can think of it as, you can define a system of linear equation like this. Okay. You can define a homogeneous system of equation like this. Okay. Now, the solution of this set is nothing but the null space. Okay. So what is the solution? The solution set consists of vectors in Rn. All right. So null space is first of all a subset of Rn. Is that clear to all of you? It is a subset of R. Now let's see why it is a subspace also. So suppose you have two vectors. Okay, let's say v1 and v2 belongs to the null space of A. Okay, which is M cross A. So that means in order to prove that it is subspace, what I need to prove is that if I sum them, their sum is also in the null space. Okay. Now what does it mean that sum being in the null space? This means that this must be equal to 0. Now why? What does now is it in 0? Is it equal to 0? So let's just check. Let's start with the LHS. So LHS is this. Now this is equal to AV1 plus AV2. Right now, AV1. What is AV1?
Zero.
Yes, AV1 is 0. What about AV2?
Again 0.
Right.
0.
So that implies that AV1 plus AV2 is also 0, which implies that V1 plus V2 is a null space. Okay. All right. Now let's check for the scalar multiplication. So this is the addition that I did. This is for addition. Now let's do for the scalar multiplication. So let's say K is in R and your V is in the null space of. All right. Now K, we need to prove that KB is also in the null space. So how do I prove that? I start with A over KB. So how do I write this? Now K is a scalar. A scalar can come out. Okay.
A into AB.
Right. Right. Now what is AB? Because AB is already in the null
0.
space. So it is 0. So it is K times 0, which is 0. K times the 0 vector. So it is 0. It's a 0 vector. All right. So this implies that KV is also in the null space. So it is closed under scalar. It is closed under the addition. So what does it mean? It means that it is the subspace of R. The null space of A is a subspace of R. Okay, where your A is M cross N. All right. Now let's find the null space of A. Okay, so we have seen an example uh, of a coefficient matrix. How do I find a solution set of a coefficient of the system of linear equation? It is same, but instead of the system of linear equation, we just have the coefficient matrix. Just think of it in this way: we just have the coefficient matrix, and now we need to find out the solution set. All right. Now, how do I do that?
R2 minus 2R1
Yes.
and R3 plus 4R1.
Okay, let me do it one by one. And then R4.
R3 plus 4R1.
Okay. So we get 1 1 1 0 0 0 0 0 0 0 4. Okay. What next?
So we can divide row 3 by 4 and interchange row 2 and row 3.
Okay. Okay. Now, do we have RREF form?
Yes, sir.
Yes, right? We have RREF. Right. Now, how do I find a basis of this? So we can think of it as that, as I earlier said, that whenever you have a matrix, you can think of a linear system of equation. How do you think of the homogeneous system of equation? Like this: AX, number of variables. In this case, how many variables will be there?
4.
4 variables. So x1 up to x4 equal to 0 0 0. How many 0 will be?
4
Like
0.
what will this be? Huh? How many?
3.
So this
3 0.
3.
Sorry. Sorry, sir.
Yes. Yes, yes. It's fine. So you can think of this matrix as system of linear equation like this, homogeneous system of linear equation, and you have solved this without keeping track of the augmented matrix because they do not change. All right, the augmented matrix doesn't change. In the augmented matrix, the last column does not change. So we can just get. You don't need to keep track of that. And then you have obtained the RREF form. So this is the RREF form of A. All right. Now I can again write it back into the system equations. Now, can anyone tell me how many independent variables are there and how many dependent variables are there in this RREF?
X1
2
and X4
independent,
are
2 dependent.
yeah.
2 independent, 2 dependent. Okay, let's go one more step further. Which one is independent? Which one is dependent?
The X1
So
and
first,
X4 are dependent.
Yes. So
First
X1,
and last
X4 are
column.
dependent. Yes, X1, X4 are dependent. X2, X3 are independent. So what I will do? So I will write it as 1 1 1 0 0 0 0 1 0 0 0 0 and x1 x2 x3 x4 0 0 0 0. Now Let's solve this. So what will you get? You will get x1, x2, x3 equal to 0, and then x4 is equal to 0. Now you can express x1 in terms of x2,
Sir, there will be
x3.
3 zeros. There will be
Yeah.
3 zeros.
Yes, yes. Correct. Thanks. So you will get this. Now what is the solution set of this? What is x1? X1 is minus x2 minus
Minus
x3.
x2 minus x2.
X2 is x2, x3 is x3 because they are the independent. They are the independent variables. So they will keep we will keep them as it is. What is x4?
0.
Zero.
0. Right. And now x2, x3 varies in R because they are the independent variables. They vary in R. All right. So this is your solution set. So this is your solution set. Or this is the null space of R. Or the null space. Sorry, null space of A, which was 3 cross 4 matrix. This is also the null space. Make sense? All right. So this is how you can find out the null space of a matrix. Okay. Right. So what you need to do, you need to start with, suppose you have a matrix A. So in generality, I'm writing. So you have a matrix A, M cross N. All right. So first step will be to think of it as that you are solving system of equation. If it is M cross N matrix, you will be multiplying a vector which is x1 up to xn and then equating it to 0. So this will be n cross 1 matrix, this is n cross 1 matrix, and this is n cross n matrix. Okay. So you can think of that you are solving a homogeneous system of equation. Okay, and then you write down the augmented matrix. Right. You can perform the row reduction operation to obtain the RRAF form. So now, once you obtain the RRAF form, so you have also noticed that the last column, which is of 0 matrix, it is independent of that. So the row operation does not change that last column. It remains 0, 0. So that column is redundant. You can get rid of that column. And you don't even need to consider that. So you can just look at A and then get the RRAF form of A by performing row reduction operation. Now, once you do that, you determine number of dependent variables and number of independent variables, as you did in this case. All right, dependents and independents. All right. Now, number of independent variables is called the nullity of the matrix. Okay, number of independent variables is called the nullity of the matrix. All right, or in other words, you can also think of it as the dimension of the null space. But you may ask, in order to find out the dimension, you need to know the basis of the subspace. But do we know the basis of the subspace? As of now, I have not discussed the basis, but you can figure out basis also. But nullity can be defined without going into basis. So what is nullity? Nullity is nothing but number of independent variables. All right. And now, once you know the nullity of the matrix, you can also express dependent variable in terms of the independent variables. From the unique rows they occur. Okay, so in our previous case, they occurred in the first row and the second row. So I use first row and the second row to write down dependent variables in terms of the independent variables. Okay.
Sir,
And yes.
sorry to interrupt, sir. Sir, what do you mean by unique rows here in RREF form?
Yeah, that's what I said, right? Dependent variables. There is only in each row there is only one leading term. Okay, and leading terms are the dependent variables. Leading term or the pivot element. So each row has only one pivot. Can a row have two pivots?
No.
Right. So each row has one pivot, and that pivot is nothing but the dependent variable. that correspond to the dependent. Right? For example, in this case, this pivot correspond to x1. In the second row, this pivot correspond to x4. So they correspond to the dependent variables. Right? That is what it means. So each unique row, so they appear in each unique row. So one row can have maximum of one dependent. That is what it means. That's why the uniqueness.
Sir, one question. Is this also part of quiz 1, sir?
No.
Okay, sir.
But this will be part of your end term.
End term. Quiz 2
and quiz 2.
Yeah, sure.
So, no. And then you can write down your dependent variables. Dependent variable in terms of the independent variable like we did in this case. Okay, now let's find out basis. Once you get the null space, you have expressed your null space in this way. Now let's find out the basis. How do I obtain basis from this? So now I have this. Yeah.
Sir, could you please explain that part in which you find dependent variable and independent variable?
So we have already recalled what is a dependent and independent variable. I've already discussed that. So when you solve a system of equation, what is a dependent variable? So each leading term in a row, there is only one leading term or pivot. That leading term correspond to the dependent variable. And the other variables which are not dependent, they are the independent variables.
Okay, sir.
So now I have this solution set, which is the null space. So now I have the null space of it. So let me write down. I have figured out the null space of this 3x4 matrix, which is minus x2, minus x2, minus x3, x2, x3, and 0. x2 and x3 are real numbers. All right. Now I want to know what are their bases. Okay. So let me just take. So what I will do, I will play a trick over here. So let me just take this vector out. Okay. This general form vector. Let's take that out. Now I see here is that there are two variables involved, x2 and x3. All right. So I want to write down this vector in terms of these two variables. What do I mean by that? So I will break this vector into two vectors so that one vector will only have x2 terms, another vector only have x3 terms. Can I do that? So I want to break this into two vectors so that first vector has only x2 terms, second vector only has x3 terms.
X2.
Do you guys have any suggestion? Yeah.
X2 0 0 0.
Minus x2, right?
Minus x2 0.
No, second coordinate also has x2.
Minus x2 0 x2 minus x3 0 x3.
So if you add these two vectors, you will get the vector on the left. This is the general. Now you have two vectors. You have obtained two vectors. Now let's see. So what you can do, you can take x2 out because x2 is the common variable. It's a scalar. So you can take x2 out. It's just a real number. So it is minus 1, 1, 0, 0. And you can take x3 also out. So it is minus 1, 0, 1, 0. Right. Now you see there are two vectors that you obtain. First vector, second vector. So what I have done is, so you can write down your null space as a span of minus 1, 0, 0 and minus 1, 0, 1, 0. Right? Now it is a span of these two vectors, and you can clearly see that these two vectors are also independent. Okay, so they form the basis. of null space. So this is one way to figure out the basis. Okay. Does everyone get comfortable with what I said?
Sir,
Yes.
sir, I had a doubt regarding basis. In the lectures, it was mentioned that there are three conditions for a vector space to be a basis. One of them was
Vector
that
space to be a basis. No, that is the wrong statement. Vector space is not a basis. Okay. A set
yes,
of vectors can be a basis.
sorry, a set of vectors
Yes.
to be a basis, it has to be a maximal linearly independent set. So
Yeah.
by maximal, it means that if we add any other vector, then it doesn't remain a linearly independent set. But can that set of vectors having one less vector or one or two less vectors be a linearly independent set?
So yes, anyone want to answer that? So he's asking, any subset of a linear independent set is linear independent? Is any subset of linear
Oh,
set
okay. Subset of linear independent is also linear
Yes, sir.
independent.
Right. But the maximality is important in this case. What do we mean by maximality? Maximal linear independent means
If we add a,
if you take any subset, yes. If you add any other, then it becomes
Then
independent.
de-
Right? Right.
dependent.
But there is one more thing. If you take any lesser, then it is not the maximal one. Right.
No.
So, but can it still be a basis?
No, because basis is maximal independent, and those three conditions are not conditions; they are equivalent statements. So having one of them is sufficient. They are not conditions to be basis. All right.
Okay.
Sir, in these cases, the base contain 4 vectors, isn't it?
Can it repeat?
In this case, the base contain 4 vectors.
No, 2 vectors. Why 4? 2 vectors.
This
they
is
are in
R4.
R4, but 2 vectors. First vector, second vector.
Okay. In R4, the base should, there are 4 vectors in R4 basis.
No, but this is null space I am calculating.
Okay.
Very,
I'm
very
asking,
confused.
asking about the basis of this one. I am asking if the base, if we find a base, it contains 4 vectors.
Basis of what? Basis of what? I've written down the basis of null space. This is the basis of null space of A.
Okay.
And basis of null space, that is what I'm figuring out, that it has 2 basis elements. That means the dimension of null space is 2. It is a subspace in R4. Right?
Okay, that I am asking. In R4, there are
it is a
4
subspace
bases.
in R4. Any null space is a subspace. That is what I proved.
Okay,
right?
okay.
Null space of A mn cross n is a subspace of R. We have proved that. Right? So now I'm finding out the basis of null space. And the way to find out is this.
That are totally different.
What are totally different? We don't get it.
Null space, basis of null spaces and basis of R4.
Yeah, they can be different because null space is a subspace of R.
Okay.
Right? In this case, it is subspace of R4. If you have m cross n matrix, then it will be subspace of some Rn. Okay, and it need not to have the same basis as Rn. Okay, that is like that is.
Okay, thank you, sir.
Yeah. All right. So, is everyone comfortable with whatever I just said over here? You can just take a general vector. You can break that vector into number of the variables that you have. Let's say you have 2 variables, so you can think of you want to break your vector into 2 vectors, so that the first vector has x2 only, second vector has x3 only, and then you can write down these things. All right. So you will get two vectors where each of the vector will be the spanning set. They will form the spanning set of the null space, and then they are also independent. So you will get the basis. Right. So that is the last step. So till this point, we have seen, we have started with matrix. We have obtained the augmented matrix. We solved this. We obtained the RREF form. We determined the independent variables, dependent variables. Number of independent variables is called the nullity. We have seen that. Now you can express dependent variable in terms of independent variables. We also did that. And once you do that, now we are left with the last step, which says, what does it say? It says that suppose x1, j1 up to xjk are the independent variables. Then you can define basis like this. Vi equal to f1 up to fn by taking xji is equal to 1 and others to be 0. Okay. So you take one by one. What do I mean by that? So this is one method that I just explained to you. This is method 1 to find out the basis. Now let's take another law. Okay. So because there are two independent variables. Okay. So we know that the dimension is 2 of null space. So how many bases we should get? 2 bases. That is clear because there are two independent variables. We know that we should get 2 bases here. Now how to get that? So we will get by this. So we know there are two bases. So let me first write down this general vector 2 times. Okay, x2 minus x3, x2, x3, 0. First time, second time, again. Okay, I have written down the general vector 2 times. Now, first time, what I will do, I will put x2 equal to 1 and x3 equal to 0. Right. So I will get what? I will get minus 1, 1, 0, 0. Second time, I will put x2 equal to 0 and x3 equal to 1. So what I will get? I will get minus 1, 0, 1, 0. All right. So I will get these two bases, which are the same as the one that I obtained just before, but this is the second one. Okay, make sense?
The second method is little bit easier than the first.
Yeah, okay. So suppose you have, let's say, so let me quickly give an exercise. Suppose your null space of some A matrix, which is let's say 3 cross 5, is given by this form. The general vector is of like this that you obtain x1, x2, x3 minus x4, x3, x4, 0. All right. So this is your general vector. So where x3, x1, x4, x2 all are in R. So how many independent variables are there?
4.
4 independent variables, right? Now let's apply method 2. So how many times I need to write down this general vector? How many bases will be?
4 times.
Yes, 4 times. Let's write down 4 times. Okay, minus x1, minus x2, minus x3, minus x4, x3, x4, 0. Okay, that's the first time. Second time also.
So how we know that there are 4 independent variables here?
Okay, can anyone want to explain that?
There are 4 variables in the null, basis of null space. So for
the null space is expressed in terms of independent variables. Okay, that is what we notice. The null space is always because what we are doing while getting the null space, it is a solution set, and we are writing all the dependent variable in terms of the independent variable. right?
Okay.
So
Yes.
whatever form you get, that will only have the independent variables, right? So, and now how many variables are there? X1, X2, X3, X4, X3, X4. So 4 variables. Because X1, X2, X3, X4. So 4 variables, 4 independent variables. Now 4 independent variables, that means dimension is 4. So you will write your general vector 4 times. Okay. So I have written 2 times. Let's write 2 more times. Okay. Suppose I have written 4 times. Now what I will do? So first I will put X1 equal to 1 and rest all the vectors to be, rest all the variables to be 0. In the second case, what I will do? I will write X1 to be 0. I will put X2 to be 1 and all other to be 0. All right. So what I will get in the first case, what I will get?
-1
Minus
0, 0, 0.
0 0 0.
4, 0. Second case, I will get -1 and then again 0, 0. Oh.
-1 0 0 0. Okay.
No, but that's a problem. So this system has some problem. Okay, so let me remove X2 from this. I think now it is fine. Okay. Just fine. Yeah, it is fine. Because if there is X2 also, then X2 must also come independent. Right. So yes, so X2 is not, yeah, so I have okay. Sorry, my bad, because I just wrote some random null space without thinking much. That's why I did this mistake. Okay, so this is the updated null space. All right. Now, how many independent variables are there?
3.
3 variables, right? Now let's do everything. So there are 3 independent variables. There is no X2 now. Okay. So yeah, 3 independent variables. So I will write 3 times now. Lesser work for me. So minus X. So X1 is equal to 1, X3, X4 equal to 0. So I will get this one. Now I will write X3 equal to 1, X1, X4 to be 0. So now you understand the point. So the pattern is you will take one variable to be 1, all other to be 0, and you repeat this process until you exhaust all the possibilities. All right. So -1, 1, 0, 0. And can anyone tell you what will be the last one? Just tell me the vector. The last one possibility will be X4 will be 1, X1, X3 will be 0. And what will be the vector?
Zero minus 1.
0, -1.
0, 1, 0.
Right. Okay. So I have obtained the basis of this matrix. Make sense? Clear? Okay. Good. So this is your step-by-step process. This is the fifth step that I did. So you write down how many. So whatever the nullity is, you write down that general form matrix, general form vector that many time, and then you take one by one variable to be 1 and the rest of the variable 0. Follow this pattern until you hit all the possibilities, and then you will get the set of pieces. All right. Okay. This I've already discussed because the last column is irrelevant, so we don't work with that. So we keep it as it is. So this is the exercise. Let me write it as exercise. If time permits, I will do this. Exercise is the following. Find the nullity of A. Find the nullity of A basis and basis of vectors. All right. You guys can handle this. Okay. So now let's recall what we did last time, because something that I'm going to discuss that we did last time, and then whatever we discussed today. So we will combine these two together and we will get one theorem. Right. So what we did last time? So last time we defined rank of a matrix. Okay. Does anyone recall? Does anyone remember what was the rank of the matrix?
The number
It's
of
also written over there.
non-zero rows.
Yeah, that is what I've written. So number of non-zero rows in the RRAF form. That's important. In RRAF form, number of non-zero rows of that matrix, okay, is called the rank of the matrix. Now, what is number of non-zero rows? Number of non-zero rows is also equal to number of dependent variables, because each non-zero row contains one pivot element, right? And that pivot element is the dependent variable, right? So each non-zero row contains a pivot element, and that pivot element is nothing but the dependent variables. So number of non-zero rows is equal to number of dependent variables in RREF of A. All right, everyone agrees with that? Is this clear? Right. Now we know that number of dependent variables plus number of independent variables is equal to number of total variables, like total number of variables. Okay, because the way we define independent is nothing but the total number of variables minus the dependent variables. That is the number of independent variables. That is what we call the dependent variable. Whichever is not dependent is the independent. Right. So number of dependent plus number of independent variables is equal to total number of variables. Okay. Now, how many variables are there? If you are working with the M cross N matrix, then how many variables are there?
N variables.
N variables. Okay. So let me write it down. So you have N variables, which is also equal to number of columns of A. Okay. So this is also equal to number of columns of A. All right. Okay. Now, what is the number of dependent variable? What do we call that? Rank of A. Right. And what do we call the number of independent variable?
Nullity.
Nullity of A. Nullity. So what we have proved is, we have proved that rank of A plus nullity of A is equal to N. So this theorem is called the rank nullity theorem. Okay, so what we have proved is the rank nullity theorem. Rank nullity theorem. Rank of A plus nullity of A is equal to number of columns of, which is N in this case. All right. Okay. So let's do one exercise before we go into this. Okay, so let's do this exercise itself, and just not finding out the nullity, but let's also compute the rank also and then verify the rank nullity. All right. So,
sir, nullity is again mentioned as dimension.
Dimension of null space.
Dimension of null space.
Yes.
Okay, then rank plus dimension is equal to number of variables. Is it work in space of nullity? We can replace
what is the
it
rank?
with.
So what is rank? Rank is
number
dimension of row space also, right? Dimension of row space or dimension of column space. This all are last. Because rank is nothing but row rank or column rank. They are same. So what is a row rank? Row rank is dimension of row space. What is a nullity? Nullity is dimension of null space. So you can also think of it in that way, but let's not think of it in that way. Just think of it in this way, that rank of A plus nullity of A in terms of nullity and rank. Now, what is a nullity? Nullity is the number of independent variables in the RREF form, or it is also the dimension of null space. Okay. What is rank? Okay. Rank is the dimension of row space or number of dependent variables in RREF. All right.
Okay.
All right. So now let's find out the rank of this matrix and the nullity of this matrix. this. Okay. And also, let's find out. Yeah. Yeah. So let's find out rank of this and nullity of this. So how do I do that? Now you should be able to tell me because, yeah.
Sir, R2 minus 2 R1.
Yeah, basically I need to perform Gaussian elimination or row reduction. Right. So R2 minus 2 R1. Okay, this will give me 3, 1, 2, minus 1, 0, 0, 0, 0. Okay, that is quick. Now, what should I do next?
R1 by 3.
R1 by 3. Okay, 1, 1 by 3, 2 by 3, minus 1 by 3, 0, 0, 0.
Interchange R2 and R3.
All right.
R2 plus R1.
All right. So you get this. Okay. So is this an RREF form?
Yes.
Okay. Why do you guys look so unconfident about this? This is RREF. Say it with confidence. This is RREF. What is what's so unsure about? Okay. So this is RREF. Now, how many dependent variables are there? How many independent variables are there?
1 dependent, 3 independent.
1 dependent, 3 independent. Okay. Because there is only one pivot element and total number of variables are 4. So 3 of them has to be independent. Right. Now, what is the nullity then?
3.
3. What is the rank?
1.
So rank plus nullity is equal to 4. That is number of columns. Rank nullity theorem satisfied. Okay. Now let's find out the basis. Okay. Basis of null space. So first of all, let me write down what is the null space. Null space of A. Can anyone tell me what will be the? Can you guys solve it on in your copy and then let me know what is the null space? Anyone?
Sir, it will be minus 1 by 3 x2, minus 2 by 3 x3, plus 1 by 3 x4.
That is the x1 coordinate. What about the rest of the coordinates?
So that will be x2, x3 like that because they are independent.
Right. Then, yeah. Is this correct? Does everyone get the same thing? Got the same thing?
No, sir.
What are you getting?
Sir, I am trying to be honest. I didn't watch the lecture, but still I am not able to do. Please.
No, I only explained in this session only.
Yes, yes, I was focusing, but I am not able to do this. Can you?
So just follow this. Express each dependent variable in terms of the independent variables. And how do you do that? So the way to do it is, the way to do it is write down the corresponding homogeneous system of equation. So all right, now it is what? It is x1 plus x2 plus 2x3 by 3 minus x4 by 3 is equal to 0. And then rest everything is 0. So you don't get anything. Now what does this imply? That x1 is equal to minus of x2 by 3 minus of 2x3 by 3 plus x4 by 3. And x2, x3, x4 are independent vectors. So they remain as it is in the column. All right, like this. Like this. So this is what, there's nothing fancy about it. It's simple. Okay. Now can you guys get the basis also? Can anyone tell you what are the bases quickly? By using method 2, obviously. Because you guys
minus 1 by 3. The bases are minus 1 by 3, comma 1, comma 0, comma 0.
Right.
And second one is minus 2 by 3, comma 0, comma 1, comma 0.
Right.
And
right.
Third one is minus 1 by 3, comma 0, comma 0, comma 1.
Plus 1 by 3.
Okay.
Right, it's plus 1 by 3. All right, you can check that your calculations.
So
these are the bases. Even if you multiply with minus 1, you will get minus 1 over there, right? Okay, you can check later also. Maybe I'm wrong or you might be wrong. Whoever, but you know that, but you guys get that, right? Does everyone get the same basis?
Sir, the number of element in the basis is equal to the variable in the null space.
Yes. Because nullity, what is nullity? Nullity is the dimension of null space. What is the dimension of null space? Number of bases. And how did I define nullity? Nullity is nothing but the number of independent variables. And you express your null space in terms of independent variables. So whatever variables will be there in the null space expression, those many bases.
Okay, sir.
All right. Now let's move on to the last topic of today's discussion. So simplest topic of today's discussion is checking if set of n vectors form a basis of Rn or not. Okay. Suppose you have n vectors given. Suppose you have 3 vectors given in R3. How do you check whether they form basis or not? Anyone want to guess? We need to use determinant. int is used determine. Okay, so when you say vectors, three vectors are bases in R3, what do you mean by that? Let's go step by step.
So they are maximally independent.
Maximally independent. Okay, good. What does it do? There are two conditions that they need to span whole R3. Second condition is they need to be linearly independent to each other, right? Definition of basis. Okay. What is the first condition? They need to span all of the vector space. Second condition is they need to be dependent, linearly dependent. All right. Now, how do we check linear independence? In one of the in the very early lecture, like in the I think the second week, we discussed you can check n vectors in some vectors in Rn by using determinant.
Sir, can you repeat
Right.
the question? Sir, like what the question asking us and what's given in the question?
So question is, does this set of vectors form a basis in R3 or not?
First check for independence.
Yes. How do you check
we
independence using
We
determinant?
have to write two of them. Cannot write A into first vector plus B into second vector plus C into third vector is equal to 0 if and only
Right.
if A and B, C are 0. Then
Right.
we can
Sir,
say that they are independent.
So also we can find the determinant.
Yes, that is what I was covering. So you can use determinant to check linear independence. How do you use determinant?
If it is unequal to 0, then independent.
If they are not equal to 0, then they are
Independent.
Right. Okay. Okay. So so what matrix? So you need some matrix in order to calculate determinant, right? It needs to be square matrix first of all. So what is your matrix in this case?
103.
3 4 1 2 3 3 2.
So you write each vector as row of the matrix. Okay. Now because you are in R3, this is a square matrix because it has you have 3 coordinates and you have 3 vectors also. So it is a square matrix. You will form a square matrix. And now to check independency, you can just take the determinant. If the determinant is 0, then they are dependent. If the determinant is non-zero, then they are independent. Okay. So what is the determinant of this matrix?
20.
1 times 2 minus 6 minus 0, 8 minus 6 plus 3 times 12 minus 3 minus 4 plus 9 times 3. Uh,
23.
23. Right? Does everyone get the same answer?
Yes, sir.
So they are not dependent, they are independent. Okay. So you can just check if the dimension of the space, that means if you are on R3 and you have 3 vectors, so you only need to check for independence. Okay. And how do you check independence? You can just check by taking their derivative. That's it. Okay. Now you can do the same thing in R4 also. So let's say you have 4 vectors in R4. How do you check whether they form basis or not? Just write them as rows.
So it is dependent.
It is dependent.
R2 minus 2 R1.
Yes. They are dependent.
Sir, if,
And if you,
in order to find determinant, if we write the rows in vectors in column wise, is there any problem?
no problem. Because determinant of A and determinant of A transpose is same.
Okay.
Right? So there is no problem.
Sir,
You
if
just
we
go
have
back to
three,
your.
so if
Yeah.
we have three vectors in R4, then determinant.
Then can you get a square matrix?
No, sir.
Yeah. So you cannot apply it immediately. You
Yes.
can only get a square matrix if you have the same number of vectors as the number of dimensions. So you don't need to check spanning it. You just need to take the determinant, and if you can take the determinant, that's sufficient. That is what it is. So okay. So now, in general, what we can say, if you have n vectors in Rn, then you can just check the determinant. You can either write each vector as the row, or you can write vector as the column. No problem. Okay, which will be the transpose of this one. You can write each vector as the column. So both will give you the same determinant. Okay, because the determinant will be same, so you can just tell whether by checking the determinant of it. There is also one method that we discussed. You can also use Gauss elimination method to check to calculate determinant, right? Or you can just use Gaussian elimination on the square matrix to tell whether if there is no independent variable, right? If there is no independent variable, that means all variables are dependent. That means the rank of the matrix is full. If the rank of the matrix is full, that means the rank of the matrix is equal to n number of total variables. Then you have, then in that case, the square matrix that has determinant to be non-zero. Okay, do you understand whatever I said? So determinant being 0 is also equivalent to having a system of equation like this. There is a non-zero solution to this. It is equivalent that there is a non-zero. There is a non-zero vector x in Rn such that Ax is equal to 0. Now this is same as saying that the null space of A is yeah, that means it's same as that the nullity of A is more than or equal to 1. Okay, so whenever determinant is 0, that means nullity of A is the nullity of A is not 0. So when nullity of A is not 0, that means what? You use rank nullity theorem. So rank of A plus nullity of A, that is equal to n. But in this case, because nullity is more than 1, so what does it imply? That rank of A has to be smaller than
N.
or equal to n minus 1. Right? So because the rank is not full means it is not equal to n. The maximum rank is n, right? And the minimum rank is 0, right? Because rank has to be positive. So maximum rank is n, minimum rank is 0. So rank is not full. Then also you can say that determinant is also 0. And how to find out whether rank is not full? You can perform row reductions and you can obtain RREF form. And if rank is not equal to n, that means there must be some independent variable, right? Or there must be some 0 row in the row echelon form.
Sir, what actually nullity represents? Like, what keywords, like what uniqueness it have?
So nullity tells you nullity is a dimension of null space. Okay. So it tells you if nullity is 0. Okay, that means there is only 0 solution. There is only 0. There is a unique solution to the system of homogeneous equation, which is determined by A. If nullity is more than 0, that means the system of homogeneous equation has more than one solution, has infinite solutions.
Sir, if it's more than 0 or
if nullity is more than 0, okay, then the system of homogeneous equation. What is that system? System is that AX equal to 0. All right. If nullity of A is 0, then this system has unique solution. All right. If nullity of A is bigger than n, then this system has infinite solution.
Sir, if nullity is 0 means there is no independent
Yes.
variable.
Yes. There is no independent.
Then there is only a unique solution, that is 0, 0, 0, 0.
Exactly. Exactly.
So, then if nullity
Exactly.
greater than 0 means there may have more than.
There may have. There is a independent.
There is at least one independent.
At least one independent. Right.
So.
Which means there is infinitely many solutions.
Infinite. Okay.
Got
then
it?
Once you relate this determinant and this nullity, can you explain that one? Determinant A is equal to 0 means that's statement.
Okay.
Sir,
okay.
Excuse me, sir.
Yeah.
If the value of nullity is a non-zero value, then it tells the number of independent variables. Like.
Yes.
Okay.
Nullity is what? Like nullity is nothing but the number of independent variables in your RREF.
Okay. Okay.
That is what I defined, right?
Yeah. Yeah. Okay. Got it.
Yeah. Okay. So now, because nullity is 0, now use rank nullity theorem. Okay. So if nullity is 0, that means what does rank nullity theorem says? Rank nullity theorem says that rank plus nullity is equal to n. Okay. So what does this mean? Let's encode this. Let's decode this. Okay. So what does this say? That rank of A, because it's a positive number. Okay. So it has to be. It can be 0. It is lower bound by 0, and it is upper bound by n. All right. When can rank be n? Rank of a matrix can be n when nullity is 0. Right?
Yes.
So
sir.
if nullity is 0, that means rank of A is n. Okay. So what does it mean by the rank of A is n? That means there are only dependent variables. That means there is no non-zero. That means all there is no zero row. All rows are non-zero. Right. So what does it mean? That the determinant is also non-zero. So if nullity is 0, that means rank of A is n, which means that determinant of A is non-zero. And if nullity is greater than 0, that means there after row reduction there will be 0. Okay, there will be some 0 row in the matrix, in the RREF, which will give us that the original matrix also has determinants. So what you guys do, you go to that lecture where I defined, where I proved determinant can be find out using the RREF. Okay, we trace back each step. Okay, so RREF form, you reduce your matrix A to RREF form. Whatever operation you perform, corresponding to each operation, you can backtrace. You can backtrace your operation in terms of determinant, and you can obtain determinant of the RREF forms matrix to the determinant of the original matrix. So if the determinant of the RREF form matrix is 0, that means when it is 0, because in RREF form, if there is an independent variable, then if there is an independent variable, then there has to be one row which has to be 0, because I'm talking about a square matrix. I'm not talking about any other matrix. I have a square matrix. Okay. So there is an independent variable, there has to be 0. whenever there is a zero row in a matrix, the determinant is 0. Okay, so now you can trace back because the RREF form matrix has 0. So you can trace back. So the original matrix will also be having determinant be 0. Makes sense?
So there is a confusion like that.
What's your confusion? Tell me your confusion.
In order to find the independence, we are checking determinant A not equal to 0, then the vectors are independent.
Right.
But here it says that determinant A equal to 0, there exists, then there exists a independent vector, independent row, but like
independent variable.
Independent variable. Okay. That in the case vector. Okay.
Is that clear, everyone? Is there any more doubt?
Sir, what is the significance of rank?
Okay, so I can tell you many significance of rank. So you just, if you know the rank of a matrix, then you not, for example, if you know the rank of the matrix, then you can tell whether it has a determinant to be 0 or not without even computing the determinant. All right. If you know the rank of the matrix, that means you know that the rows are independent or not to each other. Okay, linearly independent or not, right? Or columns are linearly dependent or not. Or what will be their column space? How will their column space will look like? How will their row space will look like? Okay, so let's say 5 significance that I told you. If you know the rank, you can also talk. You also know the nullity. So because you know the rank, you know the nullity. So you also know the solution space of the homogeneous system of equation, the dimension of that subspace. So you know a lot of things. Then once you know the rank of a matrix. So why? So what I think, like, why this thing will become important for you? I think in your data science goal, because you will feed everything in terms of data. You will feed every data in terms of vectors in matrices. Okay. Now your information of vectors will be a huge chunk of like some large matrix, okay, or some 1,000 cross 1,000 order or something like that. I don't know how big your matrix can go. And then you want to know whether you want to study all those matrices, that big matrix, or you can just have some simpler row space. So what do I mean by that? You just want to find out the basis of that. You want to reduce the independent vectors, because those vectors can be retrieved once you know the one vector. You can retrieve other dependent vectors which are dependent on that. So that's where the rank is important. Okay, so that rank will tell you that you only need to know these many vectors or these many rows. Instead of just knowing 1,000 rows, you can just only know these many rows. That's where these things get important, and then you can filter out your data. Your big chunk of data into just a small, So these are at filtration level. So, and then you can just work with ranks and get some information out of it. So that's what I think. That's one way you can put everything, this mathematical theory, into the perspective of data science. There can be many other applications. I'm not saying this is the only application, but this is the one that I can just think of top of. All right. Yeah, in case you want me to, in case you want some motivation to study all these things, so there is a motivation, but we are. I'm teaching you because if we do it in this way, then it will be helpful for you to grasp topic easily. If we, yeah. Okay, so enough with that part. Okay, so this was the last topic that I wanted to discuss. In the next session, we will be discussing which is going to be after Diwali. In the next session, we will be continuing with we will not be continuing with this part, but we will discuss the linear transformation. So this part was connected with the rank and nullity that we discussed last time. So that's why we want to finish this off in this way, so that you know all these characteristic properties of matrices. And the next time, Monday after Diwali, we will discuss with linear transformation. The new topic is linear transformation. Okay, so you guys have a great Diwali and
Happy Diwali, sir.
also. Yeah.
Happy Diwali, sir. Happy Diwali
Happy
to all.
Diwali, sir.
Happy Diwali,
Yeah,
sir.
happy Diwali to all of you. Yeah. Okay. Have a great weekend and hope to see you post Diwali and best of luck for the quiz also.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Yeah. Bye everyone.
Thank you, sir.
Bye. Bye.
Good night.
Good night also.